Welcome. So today we're going to be talking about a follow-up to our study of geometric series. And so in particular, the application I want to talk to you about is one that's really near and dear to my heart, so fractals. So my area of research is actually geometric measure theory, which has as its roots essentially creating the underpinnings to be able to do calculus on fractal sets. So I find these really fun and interesting geometric objects, and it actually turns out that for many of them, geometric series play, I'll put in a little math pun here, an integral role in analyzing their features. So I thought it would be fun at this point just to give you a little flavor of that and give you a chance to build your own fractal and then analyze it with geometric series. So, all right, here we go. So what is a fractal? A fractal is any kind of a set that exhibits self-similarity. So let me go ahead and write that down here. So it's a set that exhibits self-similarity, and I'll explain what that means in a second. Okay, at all scales. The usual definition, okay, and there isn't one strict definition for a fractal, unlike many mathematical definitions. People kind of debate between several different definitions, but one of the requirements is essentially that the set is complex enough, and the description that's often given is that it has some fractal dimension. So I'm gonna say, because I don't really want to talk about fractal dimension in this setting, I'm just going to go ahead and abbreviate that by saying and is sufficiently complex. Okay, and so for example, a line is not a fractal. Even though it does exhibit what we'll call self-similarity at all scales. So I have a gallery of examples in the next couple of pages, and we'll just go through and talk about these, and I'll highlight some of the self-similarities you'll be able to see. And so, okay, this first set here, this is what's called the Sierpinski gasket. Okay, and you can see the self-similarity here. So the set is actually this large triangle here, and then all of the smaller white triangles have been removed. So all of these white triangles are not included in the set. So the set is actually kind of the black dust that's accumulating around those edges of those triangles and the boundaries of the triangles. And so you can see this bit that I've highlighted here in yellow. If I was to go ahead and actually zoom in, right, I could zoom in on just the top piece here, and you can see that top piece looks, if I was to blow it up, it would look actually exactly like the original yellow piece. And if I was to zoom in again, right, I could actually zoom in on any one of these three smaller triangles there. And so, for example, this blue one I've highlighted, and if I was to blow that up, it would look just like the whole. And so the point is, I could zoom in really anywhere around any one of these small triangles that you see, and if I zoom in enough, I would see the same structure as the whole set. And so that's what we mean by a set that exhibits self-similarity at all scales, right? I can keep zooming in and I still see something that's roughly looking the same. It doesn't actually have to look, there are some fractals that are considered fractals. You may have heard of the Mandelbrot set. That doesn't look exactly the same as you zoom in, but it has kind of similar complexity. So I won't actually be showing that fractal here today. It's not one of the kinds of fractals that we'll be analyzing with geometric series. But let me just go ahead and run through some of these other examples. I think they're pretty fun and interesting to sort of muse over. And in going through some of these examples, we'll talk about kind of how these are constructed and in the culminating activity of this. So your assignment from this will be to create your own fractal and do some analysis on it. So, okay, so here you can see this next fractal here is the Sierpinski carpet. Sierpinski was a mathematician that developed a lot of, that first constructed a lot of these fractals. And you can see some of the similarities here, right? I have the outer square, and if I zoom in on any one of these, you can see that there are 8 squares kind of around the outside edge here, and any one of those, if I zoom in on any one, will look similar to the original square. So, and actually maybe what I will do is the following. Let me go ahead and just for picture's sake, let's try this. I will outline these. So I'll just split this up into so that you can see kind of what's happening here. Right? I have these 8 pieces, and any one of those is going to look very similar to this whole outer square if I blow this up. So you can see that actually this is true for many of these other spaces here. Let me go ahead and I'll just name a couple of these. I'm not actually recalling the name of this one here with the red square. So I'll give you the one next to it that looks kind of like a snowflake. This is the Koch snowflake curve. And the one underneath it is one actually that I'm working on a research project on. And this is a very famous space called the Loxo space. Okay, and then I've got a few pictures of some other spaces here that I'll talk about in a moment. But let me actually go back here and just comment on how you see some self-similarity here in these pictures, and then we'll talk about how these were constructed. So essentially, the idea is that this outer red square here, you can see looks very similar to any of the 5 smaller squares that are kind of filled in here. So let me go ahead and split this up in a similar way as the Sierpinski carpet, and I'll just comment that we're only considering these 5 squares as being self-similar. So and with the Koch snowflake curve, what you would notice is that if you took, say, one side of the snowflake, that this is similar, so it looks the same as if I blew up any one of these kind of smaller pieces. And I could even zoom in more And I could say this is actually going to be the same as this little portion of the curve that I've circled here. So the idea is now you can kind of see that, that there's kind of this similar structure at all scales. And you see something kind of similar with this Loxo space here, right? I can take any little segment here. Maybe I'll just take this little tiny one here, right? And that looks really like the whole thing. So that's kind of a defining feature of these spaces. And so let me kind of back up to this Sierpinski gasket, and we'll talk about how these are formed. And so let me go ahead and just describe here. There's an iterated construction. Okay, and so what I'll do is I'll start by describing the Sierpinski gasket, and then I will I'll leave it as a your turn exercise to describe the Sierpinski carpet, and then I'll talk about the ones on the next page. So, okay, here the Sierpinski gasket, our iterated construction, we start with stage 0. So the set is just going to be the solid triangle here. Okay, and I'm going to go ahead and label the side length here. The side length will be 1. So it'll be just an equilateral triangle. Okay, in the next stage, what we can imagine is, and there's 2 ways to think about moving from stage 0 to stage 1. So, so the first way of thinking about it is saying, well, let's shrink this triangle by a factor of 1/2, and let's put 3 copies of it together, right? And so if I was doing that, I would take 3 triangles, and I would glue them all together, right? And if this is 1/2 and 1/2, right, you can see that this is a solid, or this is the, as I put them together, they would fill a triangle whose equilateral triangle whose side length is 1, except for in the middle here. So another way of thinking about going from, I'm just going to rewrite this 1/2 so it's more visible. Let me go ahead and zoom in here, 1/2. Okay, so another way of thinking about this this moving from stage 0 to stage 1 is, rather than saying, well, what we've done is, rather than saying what we've done is take the original, shrink it by a 1/2, and then compile 3 copies together. Another way of thinking about this is that we take the original and we remove this center triangle from it. Okay, so both of those will give you the same thing here. And I just want to move that over a little bit. Okay, and so now let me put in, so you can kind of see what's going to happen at stage 2. Right. Well, I'm going to take 3 different copies of the stage 1 fractal. So let me go ahead and try that. So I'm going to go ahead and copy, oops, undo, let's delete that, paste, okay. Let me delete this. It might take me just a second to use this copy paste here. Let me delete these measurements. Okay, and now we'll grab this And I want to shrink it, and let's just, oops. Okay. Have I shrunk it about the right amount? I think so. Okay, and now I'm going to copy, paste, and paste, and then we will put these all together, and you can, oops, let's, all right, let's just grab that, oops, all right, let's see, move, there it goes, okay. So now what you can see then, oops, and I apparently moved this little bit here. So we'll just, all right, how about, well, all right, so there's our stage 2 fractal. You can see that I've taken 3 different stage 1 fractals and shrunk them down by a factor of 1/2. And then stuck them all together. Another way of thinking about that is if I had just taken the original stage 1 fractal and then removed from the centers of my stage 1 fractal, if I had removed, and I'll just go ahead and see if I can switch to maybe some bright pink here. If I had just removed these 3 centers, right, when I go from here when I go from stage 1 to stage 2, then I would end up with a stage 2 fractal. And so you can see that if I continue iterating as infinitely many times, so let me just write here, continue infinite. So if I continue infinitely many times, then the Sierpinski gasket is the set of points that remain. Okay, and so that's how this is constructed. All right, so I'm going to go ahead and stop the video here, and the your turn exercise will be to write down the stages of the Sierpinski carpet. How would you construct, let me phrase it that way, how would you construct the Sierpinski carpet? With a similar process. Okay, and so I'll stop the video here and we will pick up when you have done that.